A very good afternoon to all of you. Today we have gathered here for Hyperspectral Remote Sensing for Urban Areas. First of all, a very warm welcome. So this is the second last lecture in the series of this particular EduSat course for you on Hyperspectral Remote Sensing. So as we all know, Hyperspectral Remote Sensing is one kind of remote sensing that covers a wide range of spectra, that is primarily from 350 or 400 nanometers to 2500 or 2400 nanometers. We can go beyond this, but we have not been able to explore so far hyperspectral remote sensing for the entire gambit. But today we are going to talk about urban areas very specifically, and how hyperspectral remote sensing can be used in material characterization and identification within the urban area. So let us start. Why is it basically required in the urban area? Now, since urban areas is an ensemble of the natural as well as man-made targets, so if you can understand that the complexity increases because you have natural targets also. Just like soil has varied compositions. So if we were only talking about soil would be black soil, red soil, etc. Depending upon the nutrients, you could have classified the soil. But here you have the natural targets which consist of one part, that is soil. You have water. When we talk about water, we are basically talking about all kind of water bodies. So it can be lake, it can be turbid water, it can be shallow water, or it can be deep water. So the complexity has started rising now. It was different types of soil, now it is different types of water. Then we have vegetation. So vegetation, when we are talking about grass, we are talking about scanty vegetation, we are also talking about healthy vegetation, we are talking about forest. Man-made targets now. Coming from natural to the man-made targets. So within the man-made targets, you have buildings, you have roads, you have vehicles. So basically, man-made targets can be divided into three broad components. So what are the three broad components? One can be roof-type materials, the other can be the road-type materials, and the third can be the covering materials. Covering materials means the paints and all. Okay, so we are talking about urban areas, the ensemble of natural as well as man-made targets. Now, since all materials possess some unique chemical composition, and the potential of hyperspectral remote sensing is understanding that chemical composition and mapping the urban land cover through direct mapping of the urban chemistry. So what we are trying to do here through hyperspectral remote sensing is to understand the various constituents inbuilt the man-made and the natural targets, which will help us in distinguishing the different kind of targets. Now, if it had been normal optical remote sensing, when I am talking about optical, I am basically referring to the gambit of 0.4 micrometer to something roughly around 1.5 or 1.2 micrometer. When we do that kind of remote sensing and the data is scanty, that means if you have one data at 0.4, the other data is at 0.5, then 0.6 or 0.7. So that means the data sets cannot be distinguished if the scanty data is available at every 10 nanometer or every 100 nanometer. But with hyperspectral remote sensing, you have the data available at every 5 nanometer or every 10 nanometer, which helps us in understanding the characteristic dips and bends within the different chemical compositions. So this is how it is going to be useful. Then it improves the quality of retrieved surface reflectance and helps in identifying the chemical and physical properties of materials. Now that is very important because we were talking about the chemical composition. So this is how it is going to help in understanding the chemical composition and the properties. What do you mean by properties? For example, is it a freshly laid concrete or is it an old concrete? So that way we can understand the physical appearance also of the different materials present within the urban area. Now what is important to remember in hyperspectral remote sensing for urban areas is, once we will see the spectra of the urban areas, you will see that generally urban areas do not have much characteristic dips and characteristic bends. What characterizes urban areas is its characteristic feature within the SWIR, that is shortwave infrared region. So that means if shortwave infrared region is present in any spectra, it is going to be helpful in delineating different urban materials. So what does spectrum helps us to do? It permits for the quantitative and qualitative analysis. It also helps for the identification of the chemical and material properties. As I've already discussed, urban environment is very critical because it is a mixed urban environment. You have the natural as well as the man-made targets. Hence, it's a challenge for the urban areas. What you can do is you can mask out the natural areas out of your area, and you can only do the material characterization for the man-made objects. That is one kind of analysis that you can do. Achha, when we are talking about man-made targets and characterization of materials, we are basically referring to level 5 and level 6 classification of data. So you must have heard from level 1 to level 4, level 1 being the coarsest, however level 4 being the finest. When we are talking about level 1 classification, we are dealing with something like 1:50,000. When we are dealing with level 4 classification, we are dealing with something like 1:4,000 and 1:2,000. However, when we come down to level 5 and level 6, we are basically getting into the material dynamics, right? So this is how you can characterize the materials. Now, also important to understand that sometimes the materials are similar in the road as well as roof type. So how do you differentiate between these two kind of materials? So in that aspect, something called three-dimensional hyperspectral fused data can be used. So you can fuse the high resolution, high spatial resolution data with the hyperspectral data for the information that is required. Urban materials have specific fingerprints due to the minerals present within the material. So it can be due to silica, it can be due to iron oxide, it can be due to the presence of hydrocarbons. So that is what we are going to see right now. So let us see that where people have used hyperspectral data and for what reason have they used. So if you can see, they have used it for differentiating different paving materials in a city called Rome, Italy. Now if you can see, this was an old city, Rome, Italy, and it was a planned city, so it was easier to differentiate the paving materials. However, in case of Indian cities and Indian scenario where organic fashion of growth is experienced in Indian cities, it would be a little rather difficult to understand and differentiate different paving and roof materials. Then it was also used for three-dimensional urban structure, which I was already talking to you, where three-dimensional LIDAR data, that is light detection and ranging data, that gives you point cloud data or the 3D information, can be merged with the high-resolution satellite data. In this case, AVERIS was used. Now, AVERIS gives you something roughly around 5 to 20 meter spatial resolution. So, one of the most ideal resolutions to work for urban areas. Then you can also classify the urban and natural materials, and the basic classification can be the land use or the land cover. And in terms of high resolution, we will say material level characterization or material level classification. So, we omit the terms land use and land cover. We directly come and say it is urban material classification. So where it can be used? In general, when I was saying urban land use land cover mapping at a coarser level. So for example, if you are using the newest available data of HYSYS, that is at 30 meter spatial resolution, or you can use Hyperion, it gives you at 30 meter spatial resolution, that can help you for urban land use land cover mapping for urban areas as well. So now people will ask that why do I do urban land cover mapping with hyperspectral data when already optical data is available? So that is a very pertinent question. So how do you tackle that? Answer is that land use land cover mapping is enhanced when you use material dynamics, right? So many a times if you will observe that the dry river beds merge with that of concrete, many a times the road materials of concrete are exactly the same signature as that of asphalt. So that kind of differences can be obtained using hyperspectral data. So asphalt is absolutely going to be different from concrete. However, the pattern of reflectance is absolutely the same, but there is a difference in the shape. Okay, so that way it comes into picture. Then I have already said it can be used for roof type composition mapping. So in Western countries, if most of the papers that you will come across, and you will see by Herald, there is one paper. He wrote the paper in 2004 and 2006 subsequently, where he has tried to understand the different urban materials. He has tried to characterize the urban roof materials, and basically in the West they use which kind of urban materials? They use shingles, right? So a lot of pitched roof is there because of their climatic zonation. Pitched roof, you understand, they are slanting roofs, okay, and they are made up of shingles and terracotta tiles, and a lot of tile material is used, right? However, our roof materials are absolutely different from their roof materials. So let us understand with due course of time that which kind of roof does Indian scenario have, and it can be mapped, and its composition can also be mapped. The different road types, so what kind of road materials are we targeting on? So it can be either asphalt road, which in general terms is also known as bitumen, okay. Then you have tar roads, you can also have concrete roads, then you have parking lots that are cemented, yes. So that kind of condition mapping can also be done. And when I say condition mapping, I'm basically talking about whether it's a new laid or a freshly laid asphalt or an old asphalt. Similarly, it's a new concrete or a old concrete, and what is the condition? That means, is crack there? The cracks have developed. In general, cement roads and the other kind of roads will develop cracks, but the intensity of cracks is also going to tell you about the age of the road surface, right? So aging can also be detected through hyperspectral remote sensing. When I say urban tree monitoring, what I am trying to specify here is that some of the trees are very conducive for urban environment, that helps in preventing pollution, that also helps in providing shade and other kind of specific medicinal value, etc. So when people say that this particular plant, gulmohar, is there in front of your house and mango is there in front of your house, so how do you monitor that? So that can be done with hyperspectral remote sensing. And that also, for example, there was a drive few years back, eucalyptus trees were cut down from all across the cities. Now why was it so? Because eucalyptus tree extracts a lot of moisture content from the soil, okay. So the presence of water table reduces in the presence of eucalyptus tree. So eucalyptus tree was cut down. So you could have, with remote sensing and hyperspectral remote sensing, you could have managed to understand where is the presence of eucalyptus tree. So this was a negative parcel of how you can monitor the urban tree. You can also do it positively. You can try and understand which kind of trees grow in the urban scenario and which are the conducive trees, right? Okay. Urban heat island effect, very, very important, because since we all know that thermal remote sensing is largely based upon the emissivity factor, and emissivity is largely dependent upon the surface material characterization. So if you can just correlate in your mind, once you know about the hyperspectral remote sensing and the material dynamics, you can definitely correlate the heat island aspect and try and understand. Now when we say that urbanization is happening, concretization is happening, we are turning into concrete jungles, we are basically trying to give a hint that because of more concrete, there is more heat capture, and because of more heat capture, we are instilling heat within the surface, and that is rising the near surface air temperature and the surface temperature, which is rising urban heat island effects. Okay, so urban flash flood monitoring, detecting oil contaminated soil in plastic materials, how plastic materials can be used for urban areas. For example, if solid waste management has to be done, and recently in one study in Ahmedabad, we tried and found out the presence of plastic depositions within the city. So that helped us in understanding the location of the garbage, right? So that can also help us in understanding and directing or guiding us towards solid waste management. All right. So basically, I have talked about the challenges of urban areas in my previous slides, but still I would like and tell you, there are specific absorption features not necessarily available within the urban spectra that you will see subsequently in the spectra that we have plotted. Chemical absorptions are not always found in natural materials like in paint, and many a times the natural target is not detected because it is already generally coated up, right? So बहुत difficult होगा for understanding what is the surface material. It is modified by processes, urban spectra, as I told you, old and new, the presence of moisture changes, the presence of algae changes the surface reflectance. So it really becomes difficult to make out which surface was there at present. Then altered due to coatings, I've already told, and there is mixed spectral signature because the more you get deeper into the spatial resolution, it is easier for urban area analysis, but when it is coarser spatial resolution, anything beyond 5 to 10 meter is a problem for urban area analysis. I hope you understand why I'm talking about more than 5 and 10 meters, because urban areas, how do you characterize what kind of spatial resolution can be opted or apt for the urban areas? So you understand that a road surface or a single lane road in urban area is roughly around 3 meters. So anything beyond 3 meters is going to be a little difficult because it is going to give you mixed spectral signature. But it is only a rule of thumb. There can be even narrower lanes within the urban areas. It is governed by regionality. For example, USGS, if you plot all the graphs, and I was talking about Herald's study in 2004, if you just plot around all the graphs and see, they usually do not match with all the materials in urban areas. Why? Because we have been using our regional materials, however their material composition is slightly different, so it may not match, right? Spectral libraries are not easily available for urban areas. You need to build your own, and one that we have built is available with us. Then spectral collection becomes very difficult because horizontal features are different from the roof features. Yes, so if you wish to say that I want to understand the horizontal surface, it becomes difficult. Reflectance varies throughout the day, so a rule of thumb also says that you should always measure the spectra when the sun is held high at 90 degrees. So something around 11 to 3 p.m. would be sufficient for you to take the spectra. Anything beyond that will vary the sunlight and the zone, and it will become difficult for you. Okay, so let us see some of the roof types, precise spectra that we have collected during one of our campaigns of Everest NG in Ahmedabad. So if you can see that most of the roof types have a characteristic increase towards the sphere region, and if you see that marble gives you a characteristic dip at 1.1 micrometer and subsequently at 2.4 micrometer in the yellow color. Some of the materials, for example, China mosaic, gives you a feature that is closer to that of soil because the composition of any tile will come from silica. Now you see if tar, bitumen, concrete, stone and tubulin, if you can see the road types. So you see that bitumen, tar and concrete generally have the same kind of spectra. Tar is lower in spectra because of the presence of more moisture. However, when it loses the moisture, the spectra or the spectral reflectance curve increases. Yes, so any material that is going to have more moisture is going to have lower reflectance. However, any material that has higher reflectance, that means it has lost its moisture and the oily sticky component within it. Water, soil and grass, we all know now. The water has the lowest reflectance in the lowest curve, if you can see. This one, yeah. Vegetation is known to all, and soil I have related with that of China mosaic because of the chemical compositions of silica and hydrocarbons. Yes, so when we say that we can extract new and old concrete and asphalt, so what are we referring to? So if you look at the graph above on the right hand side, asphalt 1, 2, 3, 4, 5. So if you can see, 1 is the freshly laid asphalt. When I was talking in the last slide, what I was trying to mention is that what is the new asphalt is always going to have lower reflectance. It is going to have a sharp increase towards the swirl region, and when I say swirl region, I am basically talking about something beyond 1800 micrometer. However, when the sticky and the oily component loses due to aging, then the reflectance property increases. Okay. The same goes with concrete, but slightly different, or just the reverse phenomena. The fresh concrete is always going to have a very high reflectance, and you can see in the swirl band and roughly in 600 nanometer, you are going to see a slight drift in the spectral curve. However, it remains almost stagnant and shows a near dip at 1900, which is water absorption. Old concrete, due to aging, will decrease the reflectance because of the presence of what? The dirt and the dust present available. Many a times what happens is that some of the ratioing activity helps you to understand the reflectance property of materials. So for that, 490 and 830 nanometer can be used as ratioing, that is also known as visible to ratio. 830, 490 nanometer, if you take a difference, then you can come to know the effect of aging, extent of aging. Are you understanding? Yeah? No? Okay. So this would be new for you. Okay, I'll skip on this particular case study. I will take you to a fresher case study. It's a knowledge-based approach to urban land use classification using hyperspectral and LIDAR data. So what we have tried to do is, we have tried to merge LIDAR, that is three-dimensional data, with hyperspectral data. So hyperspectral data, right now we have taken not for India, it was a higher spatial resolution 5-meter data of Everest, and we have taken that for San Diego. So I'm telling you, LIDAR data and hyperspectral data. What is LIDAR going to give you? Apart from the spatial information, it is also giving you the third dimensional information, that means the height. So as per the standard corrections of hyperspectral data, so just a very quick recap, how do you correct the hyperspectral data? First, you do what? You do the geometric corrections, yes. You do the bad band and the bad column removal, yeah. You georeference the data. If it is not, then you do the atmospheric correction, because it is a contiguous data from 400 to 2500 roughly nanometer. So not only in the atmospheric window, also in the non-atmospheric window the data is drawn, right? So it becomes pertinent for you to decrease the amount of noise present in the data, because you have taken the data in the atmospheric as well as non-atmospheric channels. That is the reason why you go about with either relative atmospheric correction or you go with absolute atmospheric correction. Okay, so here in this case we have gone about with absolute atmospheric correction by radiance data. So you can see the first image, the first graph, it tells you about the radiance data. Now for everyone's knowledge, the data of any sensor is collected by the sensor in the radiance form only. Onboard calibration helps to convert radiance data to DN. Okay, and DN is encoded by the ground and given to you in the form of DN value. Now what you want is either the radiance or the absolute reflectance. So hyperspectral data is generally given to you in the form of radiance data only. Radiance is converted into absolute reflectance. So if you can see vegetation, the second graph shows you absolute reflectance. First graph shows you radiance. So radiance was converted into absolute reflectance to see the actual picture of reflectance data. So if you can see, this is a spectral curve that gives an indication that this is vegetation. Now how do you come to know this is vegetation? Because of the increase in the reflectance in the red and the NIR region. Okay. So SAM is one kind of classification, that is spectral angle mapper, which helps you to classify the image. And again, it was only a land use classification, land cover, roads, buildings, grass and trees. So we have not delineated the roads into different kinds of roads and buildings into different kind of building, but we have characterized road materials and building materials, grass and trees. So we found 73.4% accuracy. Why we did not find very high accuracy? Why? Because of one reason. The height aspect is playing an important role. So to include the height aspect, what we did, we went about with knowledge based classification, wherein we integrated the hyperspectral and the LIDAR data. So what we did, we had the Asfa spectral library, the hyperspectral data, the LIDAR point cloud data. We did the atmospheric correction and other corrections. We took out certain indices. Some of the indices which we have listed is NDVI, that is normalized difference vegetation index. Then you have NDBI, that is building index. You have NDSM generation, that means normalized difference surface model. So what is this? It's NDSM, normalized difference surface model, that means digital surface model. That means it is only going to give you the height of the buildings, nothing about the ground, nothing beyond the ground. Okay, then you did supervised classification and you compared your results with knowledge based classification. So we have told in supervised classification we got 73.4% accuracy. However, using these rules of NDVI, NDBI, you got a better result and giving you 85% accuracy. So some of the rules are depicted here, wherein we took, if it is urban one and if it is buildings, the height should be more than 1.5 meters. NDBI should be more than minus 0.5. The second rule and the third rule and the fourth rule subsequently. So this is how rule based classification can be helpful in improving the accuracy of your classification. Okay, so a quick glance at understanding the difference between SAM and knowledge based classification. So just below, right below, if you can see, okay, we'll take this example. So this is one building, and if you can see, in knowledge based classification it is classified. However, here it comes under the non-classified category. Okay. So this is how knowledge based is going to give you better results. All right. It can also help you in extracting road. However, certain misclassification was observed in KBC, that is knowledge based classification as well, but it was definitely very, very less as compared to that of SAM classification. Okay. Now, what does this suggest? This only suggests that the road were merged with the building materials, right? And here it did not happen. Why? Because we used height as a component. So incorporation of LIDAR knowledge based rules apply, improve urban classification performance. KBC successfully removes shadow between buildings for the preliminary classified image, and 10% difference of classification can be observed. Quickly take you through one of the other case studies also, where we have tried to build the urban library. Now this is also important because once you have collected the data on the ground for the urban areas, you have more than something around roughly 200-300 spectra, and you have saved all the spectra with you. But how do you come to know that the spectra that you have saved belongs to a particular category and is the right kind of spectra that you are looking forward to? So here we have used spectral angle measure, spectral distance similarity measure excuse me, for saving the data and removing the redundant spectra. So once you save in a lot of data and you take in a lot of data, sometimes what happens, the sunlight goes off, the calibration of the instrument goes off. So some of the spectra is not for your benefit, right? But you have collected the data and you have given every spectra name of concrete 1, concrete 2, concrete 3. But out of that, concrete 4 does not belong to the category of concrete because it's a mistaken spectra, right? But ultimately what you do it, you average all the concrete 1 to concrete 10, which gives you the average spectra. But it also incorporates one non-spectra, right? So for that, there is a technique called spectral similarity approach that you can do through Euclidean distance, city block distance measure, or spectral angle mapper, wherein in the first two distances, first the distance between two vectors, and city block distance is the distance vector between two vectors. Spectral angle mapper is the angle difference between two vectors that is taken to understand the differences in the spectra. So as you can see, if you see this and you plot all the spectra, you can remove one spectra. But when you see all the spectra and you do this kind of analysis, wherever the distances are more and the value is more, you are going to remove that spectra. So you precisely reject that spectra. Okay. So this way your spectral library is better than the previous library. So we tested that whether our library building was better or not. So if you can see in the middle, it is a through precise building material spectra we have classified. However, this we have classified with the conventional method removal spectra, and you can see that the better results can be found in the middle one, that is the precisely given spectra. So this gives a better classification accuracy also. So if you can see, conventionally developed spectral classification gave you 64.71, that means roughly 65% accuracy. However, spectral classification through precisely developed spectra gives you 87% accuracy. In one of the other case studies, we fused hyperspectral data with multispectral data. Now this is also one important area of research, because sometimes what happens is you have good spectral resolution, right? But you don't have good spatial resolution. So what to do? So you have to compromise either on the spatial resolution or you have to compromise on the spectral resolution for working in urban areas. But here, in this kind of scenario, you are fusing the hyperspectral data with the multispectral data. Now the methods that we have used, the three, the CN spectral sharpening, Gram-Smith principal component, these are the preliminary kind of fusion techniques. However, we have worked also on the hybrid and the Bayesian techniques, that are the advanced techniques. The results I have not shown because they are unpublished as of now. But these techniques, when were used, it gives you only whatever is the overlapping spectrum. That means if your multispectral data or the panchromatic data is only till 0.9 micrometer, then the resultant spectral dimension will also be only till 0.9 micrometer. Okay. But in other advanced techniques, what it does, it fuses the better spatial resolution with the entire spectral dimension. Okay, but here it did not happen. So the three kinds of fusion techniques we adopted, and we saw that the best fusion technique is in terms of quality metrics. After SAM classification of all the, so what we fused, let us see that. First we fused LIS4 and Hyperion. We tried and fused Sentinel-2 with Hyperion. The Sentinel-2 gives you roughly around 20 meter. We saw that the best results could be obtained in fused LIS4 data for CN, and for Sentinel data GS, Gram-Smith gave better results based on the quality indices. What were the quality indices that we had used? Some of the quality indices are bias, divergence, cross correlation, entropy, ergas, quality, RASE and RMSE. In one of the other techniques, now fusion did not give us the good results, right? Because it was only till half of the spectral dimension, only till either 1.2 or 1.5 micrometer, with which we were fusing the other imagery. No matter, hyperspectral was till 2.4 micrometer, but with the one which we were fusing was only till 1.5 micrometer, so it gave only the results till there. So we tried and understood that yes, if the second party or the second data is not giving us the entire dimension, let us do something from the image itself. So here, Averis NG data of Ahmedabad city was used, and from the data itself, that means from the hyperspectral data, that was 8.1 meter spatial resolution, we simulated the high resolution data itself. Now this would seem to you as very different, but we used some of the single frame super resolution technique, and super resolution techniques have been divided into two parts. One is single frame and the other is multiple frame. In multiple frame, what happens? The same area has been taken in different frames. So you have 4 images of the same area. Okay. So you can use the properties of all the 4 images. But here we only had one image, one single frame of that area. So we went about by using single frame super resolution technique. Within the single frame super resolution technique, we adopted 4 different algorithms: anchored neighborhood regression, sparse representation, sparse regression and natural prior, and gradient profile prior. All the 4 have different mechanisms of understanding. Okay, we will not get into the detail. We also tried to analyze the result because the enriched data was spatially enriched and spectrally retained, right? Our purpose of doing this was excuse me. Yeah. So our purpose of doing this exercise was to enhance the spatial resolution. Yeah, because it was only 8.1 meter. So we wanted to enhance the spatial resolution to something like 4 meter. And we wanted to retain the spectral information. So how do I come to know that out of these 4 methods, are all of them okay? They are increasing the spatial dimension. But are they retaining the spectral dimension? And if they are retaining the spectral dimension, is the spatial dimension enhanced? So for that we used quality metrics and we did classification at the end. Again, this is unpublished, so I'm not showing you the the entire data. If you can see in the middle, this one, this is the input data. Input LR means the input low resolution data. This particular data was brought to a scale of 4 meter and resampled to the resultant 4 meter spatial resolution. Means the 8 meter data was resampled to 4 meter, and this particular 4 meter data was then analyzed with respect to the results of SRP, SIS, and ANR and GPP. Means after simulation, we got these 4 images through the 4 methods, right? And the resultant spatial resolution was 4 meter. So we wanted to know whether through only, you could have said that 8 meter could have been resampled to 4 meter, right? It could have retained the spatial resolution or enhanced the spatial resolution, but it's not happening. If you see in the resampling, you cannot easily delineate the edges. However, in SRP, you are able to delineate the edges very nicely. Correct? So that means delineation of edges is better in the super resolution technique. So, and also by different quality metrics, we came to a conclusion that SRP, regression prior, gave us better results as compared to the anchored neighborhood regression and the others. And the data was taken for Ahmedabad. So this is one strip of the data taken for Everest NG program. For those who don't know about Everest NG, it was the Everest New Generation mission for different sites in India, flown in 2016 onwards, and the phase 2nd A part was completed this year till March. Completed last year, I'm so sorry, we have entered into 2019. Yeah. Okay, so after the best result was obtained, that means the quality of the data was assessed and we have reduced the spatial domain to 4 meter, basically not reduced but enhanced to 4 meter. So after that we went about for doing classification, and we did that with SAM and SVM for resampled image also, and for the worst and the best technique. So we did that and we found that SVM, that is support vector machine, gives us better data as compared to that of SAM. Now in this particular big wala images, you are not able to see any difference, right? So once you detail out the data, then you are able to see the misclassification approaches. Okay. So one more case study, and I suppose this is the last case study. We tried to analyze and characterize the different urban materials using hyperspectral remote sensing data. Here, the different road and the roof materials were characterized using a technique called mixture tune match filtering. So reflectance data was pre-processed for MNF components, and the MTMF technique resulted in the abundance image. When I'm talking about abundance image, that means 0 to 1. So wherever there is more abundance, the value will be to that pixel will be 1, and wherever there is low matching, the value will be 0. So roughly I'll tell you what we have done basically is, we have tried to first, we could have gone with PCA also, data dimensionality reduction. Like you have in hyperspectral data, you have more than 400 bands, 425 bands, but entire data is not of use to you, and it also improves or increases the load on your system. So what you have to do is, you have to extract that particular component within the data that has the most data, right? You could have gone about with PCA also, but PCA does not reduces noise. So we went about with MNF. MNF, PCA both are data dimensionality reduction techniques. PCA without noise, MNF with noise, right? So we went about with MNF. So some components, like roughly 7 or 8 components were taken, and then the entire MNF image was trained with certain sample data sets. For example, where is asphalt, where is tin, by the some of the study that we did in Ahmedabad. So based on that, and this is basic. Okay, I've told you. Look at this picture. This is the MTMF abundance image for the colored MTMF abundance image, where the red color, or the orange in this case, shows you the highest similarity or the greatest similarity. However, when you come to this pale pinkish color, then there is lowest similarity. This suggests two things. Number one, MTMF technique can help in understanding the various materials. Yes. So it only extracted, our basic agenda was to extract asphalt out of the total image, right? It only extracted asphalt and gave us only the asphalt roads, right? Second, the major roads were identified with a more score matching. The red color means more score matching, right? So more score matching, that means these were the main roads, and main roads are generally laid more times than the connecting roads. So that means these asphalt roads were repaired more, right? So this does not have the effect of aging. So this also tells you about the age of the roads, correct? So these roads which have most matching are the newer roads, and the subsequently which have lower score, that means they are the connecting roads. Okay. Alright, so hyperspectral data obviously has immense potential, and these are only, I think I've shown you 6 case studies. One I've skipped, so 5 case studies I've shown you. It can be used for a large data set understanding, and obviously can be correlated with other environmental indicators. And let us see what more next year would be in store for you from my end for urban areas. So thank you so much. If a picture is worth 1,000 words, and a hyperspectral image is worth 1,000 pictures. And thank you.